Professor from LHCb. He participated in discoveries of a lot of exotics. Tomasz Skwarnicki from Syracuse University.
Yeah, so thank you for this invitation. I have a difficult job of giving experimental talk to a bunch of theorists. Now, I hope you will excuse me a little bit of elementary introduction to topic of hadron spectroscopy. Many particle physicists consider this not to be an interesting topic to be working on. After all, we know about quarks from 1960s, and in principle, we have exact theory of strong interactions. But as you very well know, using that theory directly in confinement regime is not easy. Lattice QCD does a great job reproducing hadron spectrum for simplest quark configurations. Maybe postdictions are easier than predictions. These are lattice predictions from 2014, before we discovered the doubly charged baryon. So maybe it's not as precise as postdictions, but generally, pretty good agreement. The problem is with excited hadrons and also more complicated multi-quark configurations like tetraquarks or pentaquarks. These are very difficult to simulate. Lattice QCD calculations are in its infancy in simulating unstable hadrons. So most of theory so far is QCD motivated with often uncontrollable systematic errors. So there are many open questions in hadron spectroscopy. So even though we know that simplest hadrons are QQ bar and QQQ, we still don't know if diquark is well motivated by QCD concept. Is a good concept for building more complicated quark configurations and under which circumstances. We are not even sure about the role of diquarks in baryons. QCD introduced new possible constituents, gluons. So experimental situation, it's not so easy to, since they mix with normal states, it's not so easy to find a smoking gun for these states, though a lot of evidence for them exists. Last but not least, we are also not sure if nuclear type forces can bind mesons to other mesons or mesons to baryons. So, in many ways, this situation is really not tolerable. Now, most of my talk, yes?
Sorry, can I just ask? I mean, when people talk about diquarks made of heavy quarks, I thought there was pretty strong evidence that they are pretty compact objects.
Yes,
the complaint about diquarks is that they're.
This is why I said under which circumstances. There are certainly systems in which experimentally it's clear that diquark concept leads to good explanations of what we see, but what are the limits of that concept? I think that's the question. Now, most of my talk will be about heavy hadrons, and let me remind you that heavy hadrons always played very important role in hadron spectroscopy. After quark model was proposed, there were a lot of skeptics. Particles with fractional charge and so on. And what convinced everybody that quarks exist is charmonium, which delivered the whole family of very narrow states, which can easily be reproduced even non-relativistic potential model as charm-anti-charm system. So what happens separating interaction energies from masses of constituents? Picture became very clear. And we have been witnessing a second charmonium revolution for last 20 years, which often is referred to as XYZ states. The first very weird state in charmonium, which was discovered, was X3872. This is Psi2S, a pure CC bar state. And this X3872 unexpectedly right at D0 star bar threshold. It is very narrow. It is in the region that it could be a 2p state, spin 1 state. So that's one possible explanation. At this particular mass, it would be narrow because it cannot decay to DD bar. However, what's very weird is the state is right at the star threshold. There are other properties which indicate that it might be a loosely bound, people say molecular system. Yet other people insist that it could be a diquark, tetraquark. Personally, I think that's less likely because there is no obvious way to suppress its width in this model, and this would also require isospin partners that we have no evidence for. Now, one way that we can say that this is definitely not a conventional p state is that this very discovery channel that you see here, decay to pi and j psi. At the time of discovery, we had 36 events of that type in LHCb. Now we have 2 orders of magnitude more of such decays. And we recently analyzed this pi mass spectrum, which we could distinguish rho and omega. Omega is isospin conserving decay, rho 0 is isospin violating. So from this, we could determine ratio of coupling constants and compared to some isospin violation in charmonium system is expected and was measured. For example, this is for Psi2S state. That would be a typical coupling ratio of such couplings. And for X3872, it's an order of magnitude large. So natural explanation is that it has a very large this DD star bar component. Now D plus, D star minus threshold is 8 MeV higher. So this would minimize that contribution for state at that mass. Now it is a weird state because it there's a lot of properties that fit this loosely bound molecular model. And since I don't think I have time to go through all of it, I will not read this. But it also has some properties which are more characteristic of CC bar p-wave state. In particular, its production rates usually mimic production behavior of conventional charmonium like Psi2S that usually detected together. So it's possible that it's some kind of mixture of a p state and this molecular state, which could be just coincidence in charmonium if this is so, then in bothonium, it would be unlikely to find this state because a p state in bothonium are very far from the corresponding BB star threshold, so unlikely to have large mixing. Now, we know of some other states that indicate a strong mixing between conventional quark-antiquark states and 4-quark loosely bound combinations. In particular, there are two very narrow d sub s states which have masses which cannot be understood without prominent effect of these anti-meson combinations. Now, while for states like that, a lot of discussion is how much of the conventional state it is and how much of 4-quark state it is. By now, we have discovered many other states near hadron thresholds, which are narrow. In particular, the most perhaps dramatic states are Z sub B states discovered already a decade ago by Bell. These are states that are discovered in the case to charge pi and upsilons. Also, there are charge and neutral versions. Because there are charge versions of these states, there's no doubt that these are not normal charmonium states. They also have very large rates for decay to corresponding meson-anti-meson combinations. So there are ideal candidates. Now, one weird feature, okay, after these were discovered, people discovered similar states in charmonium system. So these are good candidates for these loosely bound molecular states. One feature which is a bit strange is that they peak above the thresholds. However, just cutting off. However, proper coupled channel analysis shows that poles, even though rates peak above threshold, poles tend to appear below this threshold. So most people believe that these are loosely bound molecular states, but there are also people who disagree with this. Recently, Bess discovered what are likely SU free flavor partners of this latest Z sub C 3900. So they discovered two states near this D sub S, D star, and both in charge and neutral modes. So this does look like it fits together with these states that I showed on the other slide. You probably heard that LHCb discovered evidence for pentaquarks. This evidence comes from weak decays of lambda b to J psi proton k minus, and we found very significant structures in J psi proton mass. With larger statistics, it became clear that what we see is actually a bunch of very narrow states, which happen to be right at sigma sub c d or sigma sub c d star thresholds. And the fact that they are very narrow, and also the number of states, if these are molecular states, you do expect two states here, only one here. This is strongly suggestive of loosely bound meson baryon states. Now, if this is right, then more states would be expected at similar thresholds. Some people do push this compact pentaquark models, usually with diquark ansatz. However, in these models, it's really difficult to explain why they are so narrow and why that mass splitting is such. You get it for free in these molecular models, but it really doesn't fit. They usually try to put 1 unit of angular momentum between this state and these states, but when you extrapolate from baryons, you really don't reproduce what's observed in this system. So if molecular explanation is right, we should also expect a little bit broader, but still narrow states at sigma C star D here, and maybe there is something here, and also up to 3 states here. So more data will be useful. Now, since then, LHCb has been finding evidence for states with hidden charm and strange quark in J psi lambda. The statistics of data here is much smaller, so statistical errors are very large, but there seems to be evidence for structures near this cascade sub C D star threshold. It's not clear if it's 1 or 2 states. You actually expect 2 in molecular model. It's only 3 sigma effect, so it's not an established evidence. We need more data here. Also in J psi lambda system, but this time produced not from heavy B baryons, but from B meson in J psi lambda proton system. There is a very nice evidence for a very narrow state, right at the limit of phase space here, which this is not published yet, but it was shown at summer conferences. And the mass of that state is right at cascade C D0. On previous slide, I was talking about this cascade C D0 star threshold. So this is without star here. So that's very well established 10 sigma effect. So most likely the mechanism for this state is similar as for this narrow PC 4312, which was discovered in 2019 near this threshold. That's likely as you flavor analog near that threshold.
Is there an explanation why these things should be very near threshold?
Well, if it's loosely bound, then binding cannot be large. We know from nuclear physics that this is usually few MeV per per nucleon. So you don't expect them to be far from the threshold. In this model, you also know which quantum numbers to expect, because these constituents should be in S wave, because nuclear type of interactions, that's a shallow potential well. If you put it angular momentum where you are in the continuum, right? So you only expect states when constituents are in S wave. And quantum numbers of that state, actually, this comes from amplitude analysis. So we know quantum numbers, they do fit that model. So that's a very plausible explanation. So far I picked to tell you about all these narrow states detected near hadron thresholds. There's a clear pattern that we see in the data that there are many of them. And since I started making this transparency, I had to add many new. So we continue to discover them. The fact that in bottomonium system, we see much fewer, it's just a problem that these states are more difficult to access experimentally. Many of these states were accessed by weak decays of big quark to charcoal. Now, however, I don't want you to get an impression that all the exotic states that we see can be explained as these loosely bound systems. Even in pentaquark category, we see hints of states that are not near thresholds. That's a recent evidence in B sub S decay to J psi proton antiproton. And the statistics is not great here, but there is a hint of a peak in J psi proton or J psi antiproton mass. Again, it's only 3 sigma, so who knows if this will survive, but if it is in fact a state here, it's not near any threshold. We also know a lot of broader states in charmonium-like sector. Some of these states have a long history, like for example, 4140 discovered in J psi phi decays by CDF in 2008. They claim extremely narrow state near threshold. By now, LHCb has 4 orders of magnitude more data, and we don't see anything that narrow, but there is certainly something going on at the threshold. But even more important, if you look at the Vidalit's plot, this is J psi phi, this is phi k, this is where you would expect heavier K star excitations. You don't really see bands for K stars, but you can clearly pick up very prominent J psi phi structures. Some of them may be P states, but amplitude analysis reveals that there are many states with quantum numbers that don't fit the P state explanation. So they are actually good candidates. They are somewhat broad, which actually does fit more like tightly bound tetraquark expectations for such systems in charm, anti-charm, and light quark, anti-quark structures. There's a similar story for states decaying to J psi pi, but not as narrow as from these threshold states that I mentioned from BESS. These are somewhat broader states like Z4430, which are well established by now, and they do seem to have resonant behavior. They are likely, just like in J psi phi, many of these states, we have more data that we haven't published. So some people take those as evidence for these tightly bound tetraquarks. But I must admit that even though this amplitude analysis trying to resolve all these states are pretty, fancy analysis, they are still lacking all the components. In particular, we don't yet do coupled channel fits of all the relevant channels. There's the whole sector of anomalous vector states in charmonium-like systems. The total cross-section above the d-bar threshold seems to be dominated by peaks that can be easily identified with regular CC-bar states. But if you start looking at channels in which you have narrow charmonium, let's say, and light hadrons like pi plus, pi minus, you find very strange peaks that don't coincide with any of these large peaks in total cross-section. And BESS, by scanning this region, is doing a very precise job in different channels and keeps finding evidence for more and more of these states. Now, it's possible that what we see here, that there are contributions from hybrid states. Some other people suggest that we are seeing contributions from tightly bound tetraquarks. Recently, 2 years ago, LHCb also found evidence for exotic states, not with charm, anti-charm, but only charm. This happens to be charm and a strange system, decaying to d minus k plus. No regular meson can do that. Only this clearly is signature of a 4-quark system. And you see this band here. These are conventional hadrons here, and this is exotic band. Amplitude analysis indicates that there could be actually 2 states there, one spin 0, one spin 1. So these are good candidates for tightly bound tetraquarks, perhaps with heavy diquark and the light anti-diquark. Though there are also some meson thresholds here, so there are alternative explanations as well. Recently, again, this is from this summer, not published yet, people also looked at the sub S combinations, and again, there is a faint band for in exotic channels for doubly charged system or neutral system, and the amplitude analysis wants states at the same mass as on the previous slide. So these are possibly partners of states discovered
these are
2 years ago.
These are manifestly exotic, right?
Yes, they are manifestly exotic.
Like
yes.
you can't have this flavor
No.
number from 2 quarks.
No. Yeah, all of these are manifestly exotic. So these are very recent developments. Another very recent development, only 2 years ago, first LHCb found evidence for some very significant structures in J-psi mass distribution, with these J-psis produced promptly at LHC. So instead of some smooth mass spectrum that you expect, we saw this kind of very significant wiggles. This year, CMS and Atlas confirm these structures. They even have better data than we do, while their detectors in general cannot compete with us in channels with hadrons. In this channel, all of these J-psis decay to pair of muons, which Atlas and CMS are good at. So, and they have larger integrated luminosity. So they are actually doing even better job than us. They did confirm very significant peaks there. Most likely what is happening here is that there are many interfering, perhaps interfering resonances. Some people point out that there are also a couple channel thresholds which could have impact on these structures as well. To me, it's very likely that we are seeing all heavy tetraquarks here. Now, after LHCb discovered doubly charmed barium in 2017, many people did the calculations in which they replaced this light quark by light anti-dye quark. They have same color structure, right? So very similar model calculations that reproduce this baryon mass predicted tetraquark masses for heavy light dye quarks. That's a plot from Karliner and Rosner. There was a lot of excitement that if you take two B mesons with such a light dye quark, everybody agrees that this such state would have a mass well below strong decay threshold. Also, lattice QCD people simulated that and they agree. So this state would be stable from the point of view of strong interactions and would decay weakly. Unfortunately, this is what makes it difficult to detect. Two B mesons eventually decaying quickly, a lot of final state hadrons to reconstruct. By the same slide, you can see that for charmonium analog of that state, was not clear if it would be below or above threshold. If it would be slightly above threshold, it would still be very narrow because phase space would suppress its hadronic decays. And this is exactly what we discovered in LHCb. This was work of one of our postdocs at Syracuse. He looked for prompt production of D0, D0, and the charge pi, and he found this beautiful. This is actually the narrowest known exotic hadron state, just above threshold for such decay. So this is certainly an ideal candidate for this diquark tightly bound tetraquark, which was predicted by several authors. But again, there are some meson-meson thresholds here. So for this particular state, this molecular interpretation is also plausible. Now, it turns out that for such a system with two bottom quarks, if there are both mechanisms, they would separate cleanly into two different states rather than perhaps this state is a mixture of both mechanisms. Unfortunately, experimentally, it will be very tough, but we'll try. All right, so let me try to conclude my talk. There are way too many exotic hadrons for me to talk about all of them, so I just made the selection. But I wanted you to see that, you know, what we teach to our students, that hadrons are simple, and we say everything is either QQ bar or QQQ, and we have these beautiful pictures of like charmonium with very narrow states below open flavor thresholds and predictions for many more states above. The states above the thresholds were expected to be broad because they can decay by OZI allow decays to these meson pairs. Instead, what we found over the last 2 decades is that there's a whole new zoo. Yes, there are a few states in this mass range that do fit expectations of CC bar states, but actually there are many more that don't. They are either very narrow and close to hadron thresholds, or they are broad, but they have unreasonably large transition rates to narrow charmonium and some light hadrons. So clearly, there are a lot of things going on once you exceed these 4-quark thresholds. And I think it's time for us to acknowledge that most likely we have been also cheating ourselves about pictures of light hadrons. I mean, these 4-quark thresholds for light hadrons, they come in much lower, right? Because binding is shallower. So, you know, we have been trying to fit what we see in these QQ bar or QQQ predictions, but most likely there is the whole zoo happening here that we refuse to acknowledge, and sometimes we do find strong evidence that things are happening here. A good example is this lambda 1405, which has a mass which cannot possibly be understood in any QQQ system. So people have been, you know, talking about the state for a long time, that it must be affected by this K nucleon threshold nearby. So have a 4-quark, pentaquark component in it. And maybe we should not have been surprised that this is happening. After all, from the very beginning of quark model, German told us that it's not only the simplest but more complicated quark configuration should play a role. All right, since I'm out of time, I will skip experimental prospects. So let me just summarize. I hope I convince you that recent developments, experimental developments, convinced us that we need to revisit hadron spectroscopy. Clearly, we find many states near hadron thresholds. They are narrow and fit molecular models, but there are also many more states that are not near these thresholds, broader and quantum numbers that cannot be produced by molecular combinations. So there's plenty of evidence for possibly tightly bound tetraquarks or pentaquarks. Probably the states of mixed nature exist. It will be very good to continue a very broad spectroscopy program. Fortunately, most of that physics is done by experiments which also do very other important physics. And certainly improvements in theory and understanding phenomenology of confinement would be of great value to actually help us understand the data and predict other states yet to be discovered. All right, thank you.
Amazing how much is being discovered.
Yes, I mean, it is truly amazing. We discovered like 50 new states already at LHC, most LHC.
I mean, there is just one very basic question that people often ask, since we worry about large N a lot, and at large N, the interactions between mesons are weak, right?
Mm-hmm.
But still, so can one say that these molecules can be bound by 1/n? I know there was some dispute about that, and then Weinberg wrote a paper saying essentially that it's possible. So that.
Well, you are asking the wrong person. You should ask the audience.
Yeah, I think it's an interesting question for theorists. Because, I mean, in some sense, you would say at large N, there should be lots of near threshold states, which are bound by small effects, right? Or Is that fair? Or something, I don't know if the theorists are addressing.
So what was Weinberg's argument? So now do you think these are really very delta function type states, right?
Yeah, I think it's a short paper. It's a PRL. It's already very well cited. It's from 2013. I think he basically said that if there is no channel for it to decay by fall apart, like usually you say, oh, it can just fall apart, right? But he just said if there is no channel for it to decay by fall apart, then it can be stable. I don't know, but I would need to. It's just food for thought for our collaboration. Questions or?
Yes, so you mentioned that there's been no coupled channel analysis for some of these states. Can that be problematic for?
Well, it is problematic, and for narrow states near thresholds, it's known that just doing Breit-Wigner fit is not very meaningful, that you actually need to do proper coupled channel like K-matrix fit or similar that takes into account all the channels, in particular the threshold. I mean, many of these states, they may be sitting like right below, but they have tails extending above the threshold. And in fact, when we were able to probe these fall apart modes, they are huge in terms of rate compared to these modes to narrow charmonium states, or right. So for some states like ZSAB-B, such coupled channel, or ZSAB-C 3900, such coupled channels fits were done, and it actually helps because then the peak, which seems to be above threshold, it turns out that fall is slightly below threshold, which actually fits, you know, Hadron model, right? For broader states, like let's say J-Psi-Phi or J-Psi-Pi plus from B decays, there seems to be a lot of activity in all kind of partial waves. They are not narrow overlapping, and you also have conventional resonances in the same decay modes of p hadrons. So you kind of have to do amplitude analysis, and we do. And even though we do very complicated amplitudes with up to 200 or 3 parameters, if we have large statistics, we very often do single channel amplitude analysis, which again is naive. And thresholds, even though they may not be producing narrow peaks, they may still play important role in deducing the right interpretations of broader structures that we see. But unfortunately, that's very difficult to have enough data in all the channels. Eventually, it may be possible.
How does this, some of your states compare with that from Bell, for example? I mean, can you use the data from Bell as a way to constrain some of this?
Well, LHCb is collecting all the channels on their own. It's just that you know, these coupled channels are often pairs of charm mesons. Now, reconstructing both of these charm mesons, it's difficult because efficiency is low, right? Because first you get hit by, you go after simple decay modes, but so you get hit by branching ratios, which are a few percent. But then you also have to reconstruct many more final state particles, so you get hit by efficiency. So statistics in such channels is much less than in simple channels. Let's say, you know, J psi pi is extremely easy to reconstruct in LHCb, 2 muons and a pi, all right? So statistics is disproportionate, but you know, we will have upgrades. We are in actually right now are trying to make a new detector work which will collect 10 times, will collect data 10 times faster than over the last decade. And then there's another upgrade 10 years from now, which will speed up data collection by a factor of 100. So we may actually have enough data in all the channels in the future to do a better job interpreting the data.
Great. Well, we'll look forward to more data. Thank you.